you very much indeed. Can everybody hear me clearly? Hopefully it works okay. Good. It's lovely to be back. Looking forward to an AGM tomorrow. I should catch up on my sleep a bit. Tonight's lecture, this is one of the first times I've given this particular lecture, so you're guinea pigs to some extent, so I hope it goes all right. Now I've got to do something here to get the screen on. Has that worked? Okay. Accuracy, innovation, and the advance of astronomy. Now, innovation is a word which I think you would apply to Mr. Herschel. And also his I was going to say, I always put it as assistant, which is not the wrong, his loyal. Yeah, she was more than a sister, though. I mean, she was, well, we've had this debate before. She made a real contribution to his work. And so, and his innovation, because two of the innovations which I'd point out, his real innovation, I suppose, was his mirror grinding and his telescope building, because he built telescopes that were innovatively better than anybody else's at the time. And that's why he was so successful to a great extent. But it wasn't only that. It's also because he had observing strategies that for looking for nebulae that, you know, were a new way of doing things. And Caroline, again, assisted in the way those things were done. So those were innovations. So he was an innovative astronomer, and that's one of the reasons why he made astronomical discoveries. Now, the reason for this talk, I suppose, is because I had an invitation a few months ago to write a review article for this journal, Measurement, Science and Technology, which no doubt you all read regularly. I must confess I had not heard of it before. It's an Institute of Physics journal, and they're having a centenary this year, 100 years since they started publishing. They said, look, would you write us something about what's happened in astronomy, in innovation and instrumentation and things over the year? I thought, well, yeah, that sounds fun. I'll have a go at that. So I started writing this article, and this talk is really coming out of that. Okay, so you can read all about it later in the year if you want to, references and all, if you're particularly interested. Now, what did I find? It's 100 years, 1923. I'm afraid as I get older, 1923 seems rather closer than it did. Isn't that funny? It seems rather closer than it did when I was young. Is that crazy, or do you know what I mean by that? You know, it's funny, isn't it? It's 100 years, but if I was just gobsmacked, it's hardly good English, is it? But I was gobsmacked in the end by what progress had been made in that time, and just how driven by technology it was. You know, I thought, I'll write this article. Yeah, I can find a few examples of this and that. But you suddenly find that the whole thing really was, to a large extent, not completely, but to a large extent, driven by technology, even though you don't realize it at the time. And the things which I think will, I hope, come out of this talk when I'm talking examples, I've got hundreds of examples, well, not hundreds, but lots of examples. We'll see how far we get. I can just stop at some point if necessary, or I'm dragged from the podium by my wife. So anyway, one thing that's going to be common, I think you can bring out the thread is, first is new technology, something new, some new way of doing something, some new widget, some new door is opened by technology. That's the first thing, okay? Also in this era, which wasn't true before, because you can do that in history, look at, you know, you go back and say, William Herschel, new technology. That's why he was successful, okay, the way he did his mirrors. In the period we're talking about, from about 1960-ish, I'm just below, well, around 1960 really, space, the use of space, has been absolutely transforming in the way we've done astronomy and what we found. And the third one that comes out of this, that is remarkable, is the fact of computing. Now, we've got used to now to the influence of computing on modern society, but since the 1950s, and particularly more recently, computing has been tremendously important in two ways in talking about astronomy. One is in controlling instruments and telescopes. And that's been crucial. So you'll see some of the examples. Some of these instruments we're going to talk about, very clever instruments, there's no way they could be thought about without computer control. You just couldn't do it any other way. Is there a problem I need to? Right, okay. The other one, which is more recent, but is again going to be a complete revolution, is the use of computers in data analysis. Certain kinds of astronomy require computers for data analysis. They always have, for example, radio astronomy we'll talk about later, where we've always used computers to some extent in data analysis. But that's become almost universal now, that computers are involved in very sophisticated data analysis that allows you to do things you could never do if you hadn't got that ability. So those are the main points, which I hope you'll sort of see in all of the things we talk about. 1916, okay, it's not 1920, just a bit before 1916. This gentleman was publishing some interesting theoretical ideas about relativity and gravitation. You all know him, good old Albert. And in fact, in 1916, he was talking about his gravitational theory, general relativity, with two predictions, really. One was about the bending of light by gravitational forces. The other, which we'll come to later, is about the fact that the gravitational waves could get gravitational waves in space-time, that there was sort of vibrational motion in space-time that he'd predicted. Anyway, first one, the bending of light by mass. And he'd made predictions about how much a distant star the light from a distant star would be bent by going past the sun. And in 1919, again, just before the period we were starting at, an expedition had been proposed involving Frank Dyson, who was Astronomer Royal, and Sir Arthur Eddington, again, who many of you will have heard about. He was an expert in relativity. He was the guy who said, who a newsman once asked, he said, Professor Eddington, I believe only 3 people in the world understand relativity. And he said, oh, who's the third? Anyway, to test this prediction of how much light would be bent by the sun, an expedition was mounted to Sobral in Brazil and Principe, I presume that's how you pronounce it, Principe, an island off the coast of Africa. There was an eclipse going on, crossing those points. And they were measuring using photographic plates to try and get the position of stars behind the sun when the sun was eclipsed, and the sky was therefore darker, to see how much they'd been moved, these positions, by the presence of the gravitational field of the sun. Now, that was successful. And here's one of the original plates. There's the sun eclipsed. Okay, you can see you think it's still shining, but you wouldn't be able to see that's just the occlusion disk. It's a negative photograph. And you can see some marks here of the stars they were using to see how their position shifted. And here are the actual results. And seeing as we're talking about accuracy, we'll be talking about here's minutes away from the sun and the radial displacement in some units. Here was the prediction of the Newtonian theory, and the spots are the observations summarized by this line, and the predictions of general relativity, this line. Are you convinced that general relativity is better than the Newtonian theory? Just about, I think, would be the answer. You'd like to see some error bars, indeed. Convincing error bars would be the thing. But there we are. And that was a revolution. Einstein's theory proved right, is what they said. Of course, it wasn't proved right. What they meant was it wasn't proved wrong by these observations. And it was shown that it could do better prediction than Newton's theory could. Okay, just before we start our period. Now, 1923, what could they observe? They could observe only, basically, at optical wavelengths. This is a picture showing the transmission of the atmosphere, sort of shortward into the ultraviolet. The atmosphere blanks out the ultraviolet. You can't see it from the ground. Longward, you get a few windows in the infrared you can see through. Mr. Herschel across infrared, we mentioned that, a few windows there, but it's not very good. In 23, they didn't have very good detectors there. A few photodiode, photocells, but nothing very good to detect radiation. And although they knew about radio waves, nobody had done any real radio astronomy at that time. And the transmission in the radio comes here. You can see the transmission of the radio, but this hadn't been exploited yet. So really, all our information had come just from this bit here, 23. Now, go forward a little bit in time. And in the 1930s, Jansky in the United States began to try observing cosmic radiation in the radio wavelength. And he succeeded. He succeeded in showing that there were indeed what looked like radio waves coming from our galaxy, from outside the solar system. Now, that didn't advance very far until World War II came along. And with World War II was all the development of radar, both in Germany and in Britain. It's a fascinating story. I don't know how many have read a book called Most Secret War by R.V. Jones. If you haven't read that, that's a cracking read about the development of many things, particularly of radar. And so, really, really interesting book. Anyway, at the end of the war, there was a lot of stuff left over. I'm afraid it was sort of, a lot of the German stuff was just plundered and brought to Britain for radio astronomy purposes. And during the 1950s, now nicely in our period, radio telescopes began to develop. And one of the most important things that was developed, and again, this begins to need electronic circuitry and elementary computing, is what's called an interferometer, a radio interferometer, where you use two radio dishes and combine the signals from the two of them together to give you much better spatial resolution on the sky than you can do with a single dish alone. We won't go to the we won't go into the details of that. That's a whole other lecture sometime, maybe. Anyway, that was begun to be developed in the 1950s. And here is one of the first interferometers, the Cambridge 2C interferometer. This was at Cambridge in the UK, operated at a wavelength of about 3 to 4 meters. It was active in 1952 to 55. And this started doing the catalogues of radio sources. There was a 3C catalogue, third Cambridge catalogue, which was very famous and showed up an awful lot of radio sources. Now, just zoom forward a bit in our time scale. Here's the very long baseline array, the so-called VLBA, completed in 1993, which, that's how long ago? 30 years. Are you sure about that? Was it really 30 years ago? Okay. Well, 30 years ago, it's sort of 3/4 of the way through our period or whatever. Here's, you can see a typical antennae there, and they've got one in Hawaii there, across America, and out onto the Virgin Islands, I think, out here. Very large spacing as interferometer to give very good detail. Now, you can see how things have advanced since Jansky already, and since the Second World War, and since the Cambridge experiments. Now, using this array, okay, I'll show you this rather complicated size. This is in 2005 reported. It's that telescope, that very large baseline array. What they've done, I don't know if you can see this. Can you see there's a picture of the sun there? And a line showing the path of the sun through the sky over successive days, essentially, against the background sky. And the positions, those stars there are radio sources, very distant radio sources. So this is a nice way to do the same experiment. You can look at the position of the radio sources as the sun goes by and see how much they move. Okay, now we had some error bars. You wanted some error bars before. If you ask about the deviations in these in 2005, they agree with general relativity to one part in 3 times 10 to the minus 4. So that's 1 part in 30,000 or something, that sort of. Can you see how much the errors have decreased in that? You know, you've gone from that optical thing using photographic plates, quite difficult to do. Over that 100 years, you can do this experiment to a factor in, a small percentage in 10,000, a small bit in 10,000, using a new technique, radio. To do this, you need the new technique, radio. You don't need space for this one because we can get through the atmosphere, that's okay. But you do need good data handling in electronics, or moderate for this one. Okay. Now, that's one example. I'm not going to talk about the solar system, because that would be another talk on its own, okay? But I can't resist putting something in about the solar system. Pluto, discovered in our period. When was it discovered? 1930, just at the beginning of our period, so we must put it in, surely. Not much was known about it for a long time until in 1978, coming up quite up to date, somebody noticed, looking at a photographic plate of Pluto at 2 different times, what can you see between these 2 images of Pluto? Can you notice anything? Yeah, it's distorted, isn't it? It's not symmetric. And it was realized what it was from studying how the thing came and went a bit, that they had a moon Charon. And you could do orbital dynamics and things once you knew about that. 1978. Now, space and 2015, New Horizon probe. There's Pluto and there's Charon. They're not actually that close together, obviously. This is just two images. I mean, what an advance, even since 1978. That's space for you. That's modern cameras, electronics, all the rest of it, you know. And in 1923, they didn't even know there was Pluto there. Good one. Next good one. Mr. Hubble, of whom you must have heard. 1929, there's a picture of him in 1931, looking very serious, doesn't he? 1931. 1929, he plotted the velocity of recession of galaxies from spectroscopy against the distance away. You've all heard this before, I'm sure, the idea. And that if things go faster as they're further away, it implies the expansion of the universe. An absolutely fundamental observation. And here is his data. Okay, this is distance away, that's the velocity, and there's his lines through the data. Let's have some error bars, he says. I mean, if you got this from a second-year undergraduate doing his physics class, you know, exam, you'd send him back to redo the experiment, wouldn't you?
It got 2 out of 10.
Yeah. Yeah. Well, I'll give you 3 for this, but you know. So that's how it. But on that, it was sufficiently convincing to people say yes. It looks as though the universe is expanding. Now, how far have we come since then? Here's a plot of up to about a redshift of about 0.12. I won't go to the technicalities of describing that. Most of you know what's meant by the actual numbers, but 0.12. This is around 2002. Here's distance. Here's the velocity. You've got error bars this time. Okay. Now, Hubble's original diagram is that little square there. So you were right. You were a clever boy. Okay. He knew what was going on. But isn't that wonderful how much that has been improved with proper accuracy since that time? There are various reasons why it's better. It's too because they're using a certain kind of supernova as a standard candle that you know how bright it is. Now, so that's Hubble in 1929. People have pushed this diagram much further. I'm not going to go into the details of that. Here's an example from 2018. There are various things here. It's the upper part I want you to look at. Again, redshift along the bottom, luminosity distance up there. It's no longer quite straight at the end. And that's to do with dark matter and dark energy and all these other things. It don't really become apparent until you get to a fairly high redshift. And that continues to be a very, very active area of research. But the original Hubble expansion has been perfectly shown out to about a redshift of 0.2 or so. And then the interesting stuff is beginning to come beyond that distance. Now, how have we been able to go so much further than Hubble? Well, one reason you might think about is, have we got better telescopes? Okay, Hubble used on the whole for most of his stuff the 100-inch Mount Wilson. It's 100 inches. You had to wait till about 1949, if I remember rightly, for the Palomar 200-inch. And then more recently, you've had a sort of intermediate-sized telescopes like the Anglo-Australian telescope in the 1970s, but they're only about 4 meters in size, which is the Palomar's 5 meters, so 4 meters. And until you got to the Keck telescopes towards the end of our period, which are 10 meters. Now, if I just show a diagram of that. Okay, here's Mount Wilson. okay, which is Hubble. Up there's the 200 inch. Here's the Anglo-Australian, so I say, which still did a lot of very useful work. There's the 10-meter size, which is for the Keck's. And they're, in fact, segmented mirrors, but of similar area. It's just plotted as a circle there. Okay. Now, is that a huge increase in size? No, not really. It's a bit bigger. There's more area there, a bit more area, but nothing like the sort of huge expansion you've seen in the Hubble diagram. And you won't get a really much bigger telescope until 2027, when the extremely large telescope is going to be launched. I guess it's going to come into operation in Chile from the European Southern Observatory, and that is about nearly 40 meters or 39 meters inside. And you can see that really is going to be a real leap. So that's something to look forward to. But in fact, the telescopes haven't got much larger. So it's not that. There's a picture of what the extremely large telescope will look like. Can you see these motor cars down here? So yeah, oh, I'd love to see that. Anyway, so how's it come about? Well, the answer is this. It's technology that has allowed it. When I was a postgraduate student, if you had asked me, could we ever see a normal galaxy at a redshift of 1? I'd have said no, it's impossible, they're too faint. You could maybe go to, I don't know, 0.1 if you're lucky, but no, too faint. Detection was still largely based on photographic plate and some photomultipliers. Now, in the late 1960s, early 1970s, a new kind of detector came into existence called, well, they were called various things, image tube intensifiers, photon counting systems. There are various names for them. And basically, they worked in the following way. Can you see there's an image tube at the top? I'll explain what that is in a minute, right at the top. And then some sort of other detector at the other end, and then a whole load of electronics and computing. Again, the computing again, but new techniques. Now, the image tubes had a cathode at one end. A photon comes in from the telescope, hits the photocathode, and releases an electron. You have high tension electricity down the tube, and it accelerates the electron, and it bashes into another screen and produces a bunch of electrons. Those bunch of electrons are accelerated, produce more and more and more, until this bunch of electron goes onto a phosphor screen at the end, hits the screen, and a burst of light comes out. So one photon has been multiplied to give a burst of light. Okay? Then you put a TV camera or something else to detect at the end of the image tube, and then do your electronics and all that behind it. That allows you to have a much, much higher efficiency than a photographic plate. And some of these systems in the 1970s and 1980s were very, very successful. This is one called the image photon counting system from University College. Image tube on the left, TV camera on the right, basically. And there's the circuit diagram. There'll be a test later, so just check you've memorized it. A lot of computing, but a really efficient detector that sort of can, if it's in good nick, detect almost every photon coming from the source. And it's that that's allowed you to go so much fainter for the same area of telescope. Now, that was in the 1960s and 70s. Invented in 1969, which isn't that long ago, was a so-called charge couple device. Silicon device, silicon chip. They were originally intended for computer memory, but they were found to be light sensitive if you use them in a particular way. And it was realized you could use these as very good light detectors. And in fact, you know where you've got a CCD on you, in fact, in your camera, on your mobile phone is CCD these days. Most cameras you buy are CCDs. Basically, it's an array of silicon where a photon hits the device and generates an electron again, but inside the solid. And then you can collect up these electrons and count them. So you're counting the number of photons coming in by counting the number of electrons they produce in the solid. You have to shift them in and out. And there are various ways of doing that. A simple analogy is here. You can imagine rain coming down, which is the photons, and you have buckets on conveyor belts. So you collect the rain coming in, put it into other buckets, and then measure it at the end. That's basically what it's like. But they can be very efficient, again. They can be very efficient. They're very rigid. They're small. They're lightweight. A fantastic bit of technology, which, again, allows you to observe very faintly. But you have to have a lot of electronics behind it. Now, I was saying about never observing above a redshift of 1. Well, I was a research student, well, somewhere that way. Well, around here somewhere, okay, to be honest. And at that time, these are not normal galaxies, but at that time, this redshift of 1 had not been penetrated by a normal galaxy. But by 1980 and onwards, lots of normal galaxies could be observed at high redshifts. You can see the redshift of here, normal galaxies going out maybe to 4, 5, 6. And many of you have seen the James Webb Space Telescope's recent results. That's getting galaxies now up to a redshift of 12. That's in space, of course, and with all the benefits of modern detectors. So, which is fantastic, because you're getting back then to the time at which galaxies actually began to form. So it's a fabulous improvement. Right, pushing techniques again. Do you know what these are? Optic fibers. I don't know how many of you had a play with optic fibers. Anyway, where do you get these? Yeah, in the road out there now, I expect. It's where most of your telephone stuff and internet comes on, is optical fibers with optical signals. They were sort of invented in the 1960s, and it was realized quite quickly by astronomers you could use these as light pipes. Because what you could do, it's obviously if you've got a spectrograph and you're looking at an object, you only look at a little bit of the field of view of the telescope. And if you arrange things with optic fibers in the field of view, get an automatic positioner to put them in all different positions. And here's one from the AAT, Anglo-Australian Telescope, 400 fibers, automatically positioned in about half an hour or so. And you can observe 400 spectra at once. Now that saves an awful lot of observing time. If instead of having to move your telescope 400 times and sit on each one, you can just do them all at once in the field. Obviously, it has to be in the same field of view. But that, too, has revolutionized quite a lot of the survey work of astronomy. Okay, moving on. 1965, these guys, Penzias and Wilson, most of you all know this one. This wonderfully modern-looking radio device here, in fact, was an antenna used for satellite, communication satellites. They were, trying to get stuff going across the Atlantic and that sort of thing. And as you know the story, they kept trying to beat the noise down in this receiver and this antennae, as part of which the program was removing all the pigeon droppings from inside they apparently improved it quite markedly when they got the drop. They kept on doing things, but they kept having this noise, more noise, couldn't get rid of this noise. Until they realized and got the Nobel Prize for, this wasn't noise, it was actually the radiation left over from the Big Bang, the so-called background radiation. You all know the story, I'm sure. But during our period, from 65 onwards, this background has been more and more closely observed, particularly from space, where you could do really accurate radiometry. And the maps have been improved until in 2003, they were able to find parts of the maps where they could actually see the primordial fluctuations, where, the things that the background radiation is basically very, very smooth. About 3 degrees now because it's cooled down since the Big Bang. But if you look very carefully at it, as they did by this time and beat down the errors, at about 1 part in, or a few parts in 10 to the 5 or whatever, you can see slight fluctuations in temperature, which corresponds to things beginning to go out of gravitational equilibrium. And these will be the seeds, if you like, that eventually are going to allow the collapse of galaxies. And I find this quite amazing now, what they can do. The Planck satellite, which flew around 2009 to 2013, did mapping. But what it did too, and this is a little hard to explain, but what it did was it looked over there and there, and said, well, what's the difference between these two places in temperature? And what happens if I look close, these two beams closer and closer together? And there are predictions can be made for, if you make simple models of what went on in the Big Bang, how the temperatures around these different places should correlate with each other across the sky. And the dots are the measurements. You can see error bars here. There's some error bars here. The error bars are within the dots on the rest, and you can fit. And there are not that many parameters you can fit about what happened in the Big Bang and what the conditions were and what the cosmic parameters are about redshift and expansion, the Hubble constant, all the rest of it. That is amazing. Can you see the fit? The fit is wonderful. It's not done with lots and lots of parameters. And that's an improvement since 1960, when we didn't even know this radiation existed. Again, what do you need to do this? You need technique. You've got to go to space as well. And this one too, you need an awful lot of data analysis, computer data analysis, in order to be able to pull out those results. Okay. Let's have a look at this one then. Anybody any idea what that is? Orion's belt, I think it would probably be. This is just to give you some sort of, what I'm going to talk about now is very conventional astronomy, which no doubt Mr. Herschel would have been very conversant with. Although I don't think it was his favorite kind of astronomy, and that's positional astronomy. Just mapping exactly in the sky where stars are. Now, in Herschel's time, it was a very moot point because they needed accurate positions of stars to do navigation of ships and so on. And positional astronomy was taken very, very seriously. And the way you got, well, I'll just point out here, you can see sort of typical star images here. That's about a degree, 1.4 degrees between those two. What would you say is the size of a typical star image on here? Well, it's pretty a minute. Some of these are about a minute. How about the tiny ones? A few seconds. A few seconds. Okay, remember that number. A few seconds. Okay. Now, a lot of work was done in trying to fix positions by these things called transit circles, which would be fun to talk about, but I'm not sure you're terribly interested in them, to get accurate positions. But I'd show you, this is one that, this is a picture of one from the Royal Greenwich Observatory. It was set up by Airy in 1851. I just want you to note that the date at which it ceased working. 1954. They were still using this sort of device, right, into our period, well into our period, to get positions of stars in the sky. Obviously, they would be able to do some photographic work as well, but I'll just show you another slide of it. It's so lovely. Okay, here's a trained observer using the thing, and here from the, where's it from? Does it say on here? Yes, Illustrated London News, 1923, right at the beginning of our period, showing the details of the scientific and technical stuff. This is the real hot technology in 1923 about measuring the position of the stars as the stars drift past this telescope. Now, if I show you a nice plot, there's a lovely plot here. I'll try and let you have a moment or two to absorb this. What's plotted on here is astrometric accuracy. Okay, and you have Petriman isn't here tonight, is he? You've had him, Petriman? Yeah, Perryman, yeah. He'll tell you all about this stuff. Okay, he's well known to you Barthians. That's time. It's a split. It's about 150 BC to 2000. Okay, and this is how accurate you can measure a star image to. Position, all right, on the sky. Now let's just look at the yellow line there. If you can see the yellow line, from Tycho Brahe's time, about 100 arc seconds. Well, by about 1830, Bessel had managed to measure positions to about 1/10 of an arc second-ish, and had managed to see the first parallax. And you all know what parallax is. The sun goes round from one side of its orbit to the other. If you look at a nearby star, its image shifts across the sky very slightly on a 6-month scale. And he was therefore able to measure the distance to that star from the geometry of this. Now, things got better and better, but by 1900, we're still, if you look at that yellow, we're still around maybe a bit less than an arc second general, around an arc second for general positions. Even to, if we go to 1950, we're not doing very much better. However, if I put in a line at 1990, right, when the Hipparcos space mission flew, first in space, right, that helps because you haven't got the atmosphere in the way. Look how the accuracy comes whamming down, or whamming up, I suppose, accuracy. Errors come whamming down. Hipparcos mission, which was 1989 to 93, began to measure positions to about 1,000th of a second of an arc. The Gaia mission, which is working from, have I got it here somewhere? There we are, the Gaia mission, which is working from 2013 onwards, and I'm sure you've had to talk about Gaia mission, haven't you? Yeah, okay, so I won't need to say a lot about it. Is getting positions to a microsecond. Okay, and the fascinating thing is, and I just find this just wonderful, is it's incredibly simple in concept. Technically, it's wonderful. Yeah, it's very complicated, but in concept, all it does is it looks at a bit of the sky there, and it looks a bit at the sky there, right? Two telescopes like that, essentially, and lets the images from both telescopes drift across a whole lot of CCDs. Okay, so, you know, what happens is just the images go across on both telescopes across the CCDs. The thing spins around and looks at different parts of the star, and all the time they're just going across these CCDs, just going. What you do is you just note where they are, watch their track, and time them. That's it. You don't have to do anything else. You just have to observe where on the CCD they are and follow those positions with time. For orbit after orbit after orbit after, scan after scan after scan. Now, you do then need a computer. Okay, and the data analysis, you can imagine, is horrendous. But if you do that, and do the computer analysis on those positions, you can get positions to a micro arc second, and all sorts of other things too, how things have moved, and motion across of stars across the sky, and all sorts of things. Now, in terms of our old parallax for a moment, here's a rough, this is a sketch I made while on the spaceship on my holidays last year of the galaxy. And here's the sun out here, okay? Now, remember I said Bessel did this parallax. By 1970, parallaxes were, a few thousand stars were known to an accuracy of about 0.01 arc seconds. And that would allow you to look, 50 parsecs, whoops. Oh gosh, where are we? 50 parsecs away, okay? That's 50 parsecs from the sun. That's how accurately you could get your distances in 1970. These new satellites, Hipparcos and Gaia in particular, you can see that far and get accurate distances right into the center of the galaxy. That's a real revolution. There are billions of objects in there with this detailed knowledge of their position, their distances, their motions. And once you've got motions across, then you can do the three-dimensional geometry of the galaxy and so on. So, three-dimensional kinematics, fantastic. Okay, next thing, adaptive optics. Have you had a chat on adaptive optics before? Right, you'll need a course on that, I'm afraid. Basically, it's quite, you know, it's taken a while to do it in detail. I'll just give you the very basics. Very clever. It sort of took off in the 1980s, 90s, and is only now really being exploited. What you do, and the idea nowadays, what you do is you use a laser, and you fire up a laser. You can see that at the top. You fire up a laser into the atmosphere, and at about 90 kilometers up, it excites sodium atoms and ions up there, and they radiate. And that gives you an artificial star up in the sky. And you collect the light coming back, and you put it into what's called a wavefront sensor. that looks at the telescope mirror and says, oh, the light from that star, that artificial star is coming in there, 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 there. That's slightly different from that. That's slightly different from that. You feed that information back to a deformable mirror in the optics train. Now, a deformable mirror means it can flex a bit. Do this. So if you sense the way the wavefront's been distorted by the atmosphere, you can push it back a bit into condition. Okay? And the light from whatever you're observing near the guide star or near the artificial star can then be observed with your instrument, but with its image shrunk down as though the atmosphere wasn't there so much. Does that make sense to you? Okay, that's good. Okay, you need a powerful laser. You need a very powerful laser. Well, lasers weren't invented till when? You cheated. Okay, not invented till 1958, so you couldn't, and obviously nothing like these high power ones till fairly recently. So you need that, and you need an awful lot of electronics, an awful lot of computing to do this. And you need good image sensors, which again rely on things like CCDs and all the rest of it. So the one I'm going to show you, the results I'm going to show you, are from the Keck telescope, which has this is the diagram of its Keck, the Keck laser guide star. So, you know, you don't want to know, do you, basically? There we are. You can actually see the two Kecks there throwing up their artificial guide stars and observing up over there. Now, to give you some examples of that in working, here's a 0.3 degree binary for those of you who enjoy your observing. That's without wavefront correction. That's with wavefront correction. You see the difference? Okay, it's extraordinary what it can actually do. And one more from planetary stuff. I can't resist showing one more planetary slide. This is Uranus. Hello, William, are you watching? Look, Uranus with its rings you didn't know about. Okay, but look, that's with the adaptive optics system off. This is normally done in the infrared because it's easier to do in the infrared. And there's with the adaptive optics system in working. Can you see the difference in detail? You can see the stuff on it. It's phenomenal what it can actually do under the right circumstances. Okay, now, adaptive optics, we're now going to go on a journey. Okay, and we're going to go into the center of the galaxy, into Sagittarius. We're zooming in. William would have loved this. Okay, we're going in, going in, going in. Going in as far as we can on this. It's very dusty in there. We need to go to infrared wavelengths in a minute. And about there is where the galactic center is. Okay, viewed from us. Let's have a look at that. Now, it was known from about 1974, nicely in our period, not that long ago, 1974, that there was a radio source at the center of the galaxy, a strange radio source. It was called Sagittarius A star, and it's about 8.4 kiloparsecs away at the center of the galaxy. Okay, now, using the Keck adaptive optics system, okay, here is a region of the center of the galaxy. Now, this slide here, that's 10 seconds by 10 seconds. Now, what did we say the size of a typical star image was on those photographic plates earlier, or if you look through a telescope? You'll be lucky. 2 to 3. 1, 2, 3, something like that. But look at this. I mean, that's one is that. Okay? So, and here's something, 1 second by 1 second. So a normal star image is bigger than that whole picture. But can you pick up? You can pick up objects here. And that's showing that slightly yellowy thing there is the radio source, or where the radio source is, at the very center of the galaxy. Now, the work the Californians have done, it was two teams, one from California, and one from Germany. Andrea Getz led the one in California, Reinhard Genzel in Germany. Now, what they've done is they've looked at that central region, all right? And they've observed the stars in that central region. You saw them on the picture, but they've observed them over many years. Okay, initially they didn't have the laser system, but they managed to do some stuff without the laser system, and they've gradually improved things. And what they've done is they've actually plotted the orbits that they see of the stars over the years. It's just beautiful classical astronomy. You know, watch the star, plot it as it moves. And I want you to look, SO2 is the one we're going to look at in here. I'm going to show you a movie. I hope it works. Okay, we're going to watch SO2. Can you see? There's the center with the star, the sort of five-pointed star. It doesn't, the galactic center doesn't actually have a five-pointed star before. Anyway, SO2, can you see it just above there? Okay, keep your eyes on that. And we're starting off in 1995, okay? You ready? Right. Hope this works. Go on, damn you. Children and animals. No. Is it going? What the hell's wrong with that? Oh, I'm sorry. For some reason, this isn't behaving itself. I'm just going to go back and try again. Okay, watch it. You're watching SO2. That's that one there. Watch it right around the center and out. 2003, 2004, 2005, 2007, 2008, 2010, 2011, 12, 13, 14, 15. Watch it come back in again to 2017, 2018, 2019, and round again. And this is, how big is this? It's smaller than the typical image of a star. And this is, I just find this breathtaking. And what's so wonderful about it is you've just got a star orbit. You can then calculate what that's orbiting about, how much mass there is there. And you'll find that there's a 10 to the 6 or 10 to the 5, whatever it is, solar mass black hole in there. And also you can observe in the orbit the relativistic effects as well, just as you did to some extent like the light bending effects around the sun. I just think that is extraordinary work to be able to see on such a tiny scale and get very direct estimates of this black hole. Of course, we didn't know anything of black holes in 1923. It's amazing. Okay, and other things have been from 2019. There's a thing called the Event Horizon Telescope, which is again a radio interferometer all around the world. And using that, they've got an image of that Sagittarius A radio source in more detail. And here's it. So the yellow is what you see in the radio, and that's how the black hole of the sun is where I put the sun, that spot at the middle is where the black hole is. But that spot is plotted as the size of the sun's diameter, which on cosmic scales is pretty small. And you can see Mercury's orbit there, if we were at this distance. So what you're seeing here is the accretion disk around the black hole. You're actually seeing that. And this will no doubt feature next talk with your chef who's going to show you how to feed black holes. You'll no doubt see this again. But again, this is extraordinary to be able to get to this sort of length scales and observe these length scales and actually see these things is, I just think, quite stunning. Okay, I'm running out of time. I don't want to go on too long. So exoplanets. Next thing, nobody had any idea about in 1923. There would have been speculation, but nobody knew whether they were exoplanets. People started looking very carefully at the sun around 1960 and being able to just about detect movements of about 1 kilometer per second on the surface in terms of velocity changes at radial velocity. And a guy called Peter van der Kamp in 1969 claimed, looking at a nearby star, that he could see a wiggle in the motions the star moved slightly across the sky that he thought was due to exoplanets. It wasn't, because I've plotted on again the size of a typical star image at that time. So his wobble was just noise, unfortunately, but it was a good try to be able to find exoplanets using that technique. And the way exoplanets were actually discovered was from observing binary systems, what would like a binary system, observing a star and with a planet going around that causes slight forward and back motion in the star. But the trouble is the motion in the star it induces is very, very small. If I was looking at the star, I'll show you now. I'm showing you, you can see clearly the changes in the spectrum here as the star is orbiting, can't you? You can see how the lines are changing very markedly as you can't see a thing, can you? That's what you'd see. Nothing, essentially. Unless you use very, very sophisticated techniques. You have to have extreme stability in your spectrograph. You have to have a very good reference spectrum, and people began to use reference spectrum by using the spectrum of iodine sort of superimposed on that. And then you could try and measure tiny, tiny shifts between that stellar spectrum and the reference spectrum. Technically very difficult, but achieved in 1995. And some astronomers in 1995 did manage to do that and actually got this curve, sinusoidal curve of the velocity of the planet, the motion of the star caused by the motion of the planet. But can you see the velocities we're talking about? We're about 50 meters a second here, not kilometers a second. You're measuring to meters per second here. And that then allows you to discover planets. And as you know, I won't go into the details. We know lots and lots of planets now. And that's a whole talk in its own right. But we had, as I say, until this happened, we didn't know whether stars really did have planetary systems or not, but they do. Nearly all of them do. And that's great for the future. What's also lovely about this, nobody had any idea what the properties of these planets would be. Everybody said, oh, everything will look like the solar system. Didn't look at all like the solar system. Completely wacky and out the way. It's a wonderful story. Anyway, okay, and that's where the Earth is on that diagram, if you're interested. But anyway, okay, let's move on. Now, remember I was talking about Gaia and how accurate it could do positions. Do you remember what the microseconds? Well, of course, you can do what Peter van der Kamp tried to do with the wobble of the star moving across the sky. But because we're so much more accurate in the positions, here's a particular star and its position on the sky observed over time. And indeed, you can actually see on some of the stars, you can actually trace the orbit caused by the exoplanet. It's another way of doing it apart from spectroscopy. You can actually do it by now, because you've got the new improved accuracy, you can actually see the astrometrical variation. They actually follow the orbit around the thing. Okay, I've got time just for one last thing. 1974, two astronomers discovered, Hulse Taylor they were called, discovered a binary pulsar. Now what they meant by that is they found two neutron stars in orbit about each other. They couldn't see one of them. The other one was a radio pulsar. And I'm sure you've all heard of pulsars. They're rotating neutron stars that generate radio waves, and the radio wave flashes past you and causes pulses. Now, if you've got them in a binary system, it's wonderful because you've got an orbital system there, but the pulsar acts as a very accurate clock in the system. So you can use it as a very accurate time reference in studying the motion of the system. And that turns out to be wonderful. Now, they found this binary pulsar in 1974, period of 59 millisecond, and you can see its orbit period, and that's the error bar on that for a gentleman here who loves to have a decent error bar, and that is a really good error bar, isn't it, to get things to that accuracy. Okay, it's about 8 hours the thing goes around. Using that sort of information with this very accurate clock in there, look what you can discover. Look at the accuracy of the ellipticity of the orbit, how elliptical the orbit is, and the masses, the individual masses of the stars. You can get to, look at the astonishing accuracy you can get those masses to. I think that's more accurate than we've measured the sun to, probably. But it's fantastic. Now, what they did also was they followed the orbit over time, and the orbit of the two is decaying slightly over time because a system like that, as it goes around, these massive stars going around, or not that massive, but those stars going around, will warp space-time. And if you warp space-time in that way, it sends off waves, gravitational waves, into space-time. And they measured the change in the orbit over, what's here? This is change over 30 years, 75 to 2005. And they're the spots. You don't really need error bars on these particular spots. That's the general relativity prediction of how the orbit would change because of the radiation of the gravitational waves. Virtually nothing fitted, just the mass of the stars which we've got in other ways. That's the prediction of how much the orbit would change just because of the radiation of gravitational waves. So 74, though they did this, fairly soon after this, they began to realize that was happening. Here's over a good time span. It shows that gravitational waves exist because you can see their effect in this pulsar, okay? But you haven't really discovered them, have you? Or have you? You know they're there, but you haven't really seen them. And the last thing I just want to mention is the detection of gravitational waves. And you remember we saw Mr. Albert at the beginning of the talk, 2016. And what did he predict in 2016? Gravity waves, okay? And by about 2008 or so, people have begun to build detectors to try and find gravitational radiation. Now, if you want something ultra tech, this is your baby, okay? 4-meter long evacuated tubes at something like, I can't remember, I forgot the thing there. Yeah, 1 micropascal, which is about a tiny bit. An atmosphere is 10 to the 5 pascals. You have to have a micropascal in the tubes so that the light won't scatter in the air. So it's a huge ultra vacuum in there. Mirrors at either end. I was going to say a rude word then. It was a technical term meaning very big laser. Okay, you have to have huge laser powers pumping into this interferometer. And what you observe is as a gravitational wave goes through, it stretches one arm slightly and compresses the other slightly. And you measure the difference between those. The measurement accuracy is equivalent to, it's not exactly the same as, but it's equivalent to measuring 1/100th of the radius of an atomic nucleus. It's a tiny, tiny length difference, but they can do it using this technique with these huge lasers, modern optics, and so on. There's a picture of one of these interferometers. It's out in the desert. You can see the two arms there. And indeed, just to give you some idea about this is what you might expect. The way the thing goes, you get some signal that looks like that wavy line there. What you're doing over 4 kilometers is looking for the strain. And the difference, as I say, is this tiny, tiny, tiny amount. But it can be detected. And it was detected for the first time in 2015. And that's the theoretical signal. That's what they detected. You can see the similarity, but there's vast amounts of data processing in pulling that out of the general vibrational signals of these interferometers. And that detection was believed to be 2 black holes, quite large black holes, about 36 and 29 solar masses combining, and producing another black hole, and radiating away 3 solar masses worth of energy in gravitational waves. So, 1923 to 2023, I think you see some incredible astronomical discoveries, most of them unanticipated in 1923. And what's been common, as I say, it's the technology very often has allowed this, some new technology. The image tubes, these image intensifiers, getting into space, getting computation on all of these things, new technology, getting into space, computing both for instrument control and data analysis. And I found it quite interesting just how far these incredible discoveries are based on technology and how they've been driven. And it makes you wonder what's going to happen in there if I come back and give the same talk in 100 years, which will require some very special new technology to get me back in 100 years. But thank you very much.
Thank you. We'll take some questions. We'll get to the room first, and then we'll go to the Zoom after we've had a few questions from here. With this microphone, please speak directly into it. It's very directional.
Thank you. Hello, Mike. Thank you. Really interesting talk. Loved it. My youngest daughter, she'll be 2 next week. If she lives to be 100, what might she see in her lifetime?
One might predict 10 years ahead, try to predict 10 years ahead. 100 is more difficult, surprisingly. 10 years ahead, a lot more known about the surfaces of Mars, I would suspect. We'll know a lot more about gravitational radiation and its sources. I think the parameters of dark matter and dark energy will have been pinned down a bit more, but I don't think we'll know what they are. So what I hope perhaps by 100 years' time, there might be some notion of what these dark energy and dark matter, which I haven't really talked about today, but you know about the big problems, are. But I think it may be on that time scale before we know those things. So if she can give us send a message back in time, that's what I would guess would be the hot things. And the other thing, of course, is all the things we haven't discovered yet. I mean, 23 pulsars were completely unknown. Neutron stars were a complete figment of the imagination. Black holes were a concept, but not detected. So,
Mike, well, I hope that she becomes a scientist, and when she gives this lecture, when she's your age, I'll make sure that she mentions you, makes a reference to this. She says that her dad was here in 2023 to see the great Mike Edmunds deliver his oration to a room of applaud.
Thank you very much. History in the making. Yes. Good luck with her. Yes.
Going back to your slide with the different size of telescopes, if you compare the James Webb telescope to the extremely large telescope, what will the extremely large telescope do that the James Webb can't?
Well, they're very complementary in a way, because the James Webb is a bit smaller than the Anglo-Australian telescope, if I remember, which is the 4-meter one. So it's about 3.6 meters, I think. Anybody can remember exactly? It's small comparatively, although it's large compared with what's been launched before. It's bigger than Hubble. The James Webb is very cold. That's why it was put into space. So it can do very good infrared astronomy without having noise from stuff. It's outside the atmosphere, so that means it can see quite a good detail. But it hasn't got the area that the very extremely large telescope will do, which means the extremely large telescope can collect a lot more light. Okay. And for some things, some spectroscopic studies and so on, there will be a gain there that will allow things. And with some of this laser adaptive optics and things and so on, their image quality may be comparable with Webb. So the Webb gains because it's in space, very low noise, cold, whatever. The ELT gains because it's on the ground but has huge area. And that's basically, so they're to some extent complementary.
Is there a risk that the technical ability to produce these machines just runs out? I mean, everyone was terrified when the James Webb was launched with all the various things that had to happen correctly to enable it to function. They did, but, you know, there are lots of fingers being crossed. Yeah. And then we have the extremely bloody huge telescope being built. I mean, will there be one beyond that? I mean, don't you get to the point where you can't make it bigger? So then the question is, perhaps you can actually measure what comes out of it more finely. Yeah. Well, where's the future gain?
Yeah, I'll answer your question. I obviously don't know, but what I would say, there's one here in a moment, that what I would say is that what have I been pushing all through this talk? New technology, something that hadn't been used before, allows something. And if you at any time said, well, with our existing technology, what can we do? You could do a few more things, but then you'd stop, as you say. But what comes along, we hope, always, is new technology and new ways of doing things. And that's what allows you to go further. And you, as I say, you can guess that for a few years in the future, but you can't really project very far in the future. So I think, yes, there will be things beyond that. What they will look like, I don't know. I'm giving you could do a 40-meter telescope, which is this bell. You could probably, if you really tried hard, make 100-meter. Be difficult, but 100-meter. But as you say, by that time you think, well, no, actually, we're not going to do our astronomy that way. We're going to do it in a completely different way because of new technology. So I don't think it will stop. So long as we remain curious, so long as we don't destroy ourselves, okay, and so long as money is spent on it, and in terms of actual international money, it's not that much of the gross national product of the world. So long as we do those things, I think it'll keep on. There's a question here. At least I hope it will.
Yeah, my question is directly follow on really about new technology. Clearly, some of the new technology has just come along. So you don't use special computers. You use the best ones that are there for commercial purposes. But things like the intensifier tubes, they're like what the military use on a rifle, but they're specially developed to do what the astronomers want. Yeah. And I was going to ask you about the CCDs that you use. I mean, they're in all our digital cameras and they're in solid-state TV cameras, but are the astronomical detectors specially made?
Some of them are, but that's an interesting case because as I understand, I'm not an expert on the history of this, so I'd have to go away and research it a bit. But as I understand it, the astronomical input was very important. They weren't developed for astronomical purposes, but astronomy realized it could use them and began to use them. And then commercial people realized, these have got other properties. We could use them for other things. And then they developed from cameras and so on. Yeah. But the actual technical specifications, say, for what you need in your camera on your phone is very different from what you need for an astronomical device. But obviously the foundries, the expertise and so on was developed in parallel. And so, you know, which has benefited everybody, basically.
Yeah, because I remember there was when they moved the Isaac Newton telescope to Hawaii, was it?
La Palma.
Yeah, La Palma. They built a special CCD which cost £1 million. And I suspect it's
probably a lot cheaper now.
Yeah.
Well, I can tell you, just on that, I'll tell you a story very quick. It'll only take a moment. Is when I used to be on the research council committees and so on, and when we were beginning to consider the possibility of this gravitational wave detectors, right, the big ones, we had various theory groups who wanted to do calculations to, you know, work out how you would detect these things, and they put in, I think it was a grant for 10 terabytes of memory to do this, right? I remember the grant coming on. And we ummed and ahed and we thought, well, this is going to cost us hundreds of thousands of pounds, or at least, I think it's hundreds of thousands of pounds to supply this thing. I can't remember what the decision was in the end of what happened with the grant amount. You can go down to Smith's or whatever in the high street now, and you could buy 10 terabytes for, I should think, under £100. I mean, it is extraordinary. Some technologies just take off, and obviously for the interferometers, this was fantastic news because it really brought the computing costs right down and tractable. And same for the Hipparchus and Gaia missions, computing costs came down, and that really meant that you could do the data processing, which otherwise would have been prohibitive.
Hi. Well, first of all, an observation. One thing that struck me has been like over my lifetime, the way in which technology has been brought within the reach of amateurs, and the huge advances in, for instance, the quality of images that are now within the reach of amateurs.
With small indeed, commercial CCDs. Yes.
So moving on more to a question. Okay. Okay. I'm aware that the James Webb Telescope, I think it's got a mission life of 20 years, and I'm sort of intrigued as to what the successor mission might be. I don't know if you've got any thoughts about that.
I believe it is being talked about, but I haven't really followed it. The trouble is, I'm really looking forward to all the web, and they say 20 years. The next mission beyond that, I'm not sure I'm going to see an awful lot of. But I'll get interested.
So
when it comes closer, I'll get more interested.
You're less interested in that.
Yes.
One thought I have is you talked about the use of interferometry, and would it be possible, to have baselines across space?
Yes, is the answer to that one. There are definite proposals to put a gravitational wave detector into space, the so-called LISA project, which would be free-flying interferometers. But you could think of free-flying stellar interferometers, optical interferometers, free-flying radio interferometers. Particularly for radio interferometers, the current mantra is to put them on the backside of the moon, because you've got, you can put them on the surface there, and you can make them large, but not larger than on Earth, I suppose. So that would have less interference. But there's no reason why you shouldn't do free flying stuff. Yeah.
Right, we have a question from the chat channel from Maggie Collins. She asks, another new development is the citizen science projects, such as Galaxy Zoo. Herschel started as an amateur. Do you think that these citizen science projects will add to our knowledge and to public involvement with astronomy in the future?
Well, they already have added to our knowledge. Some of the galaxy recognition stuff they've done is very good, finding unusual galaxies. And I'll pay tribute too for amateurs who've done it not only in citizen science, but over the years, observing double stars and variable stars. They've got the time to do this and alert professionals and so on, and that's been extremely valuable. It'll happen a little less once some of these automatic telescopes scanning the sky every night and data processing that will get more signals than amateurs. But no, there are still particular niches in which the amateur contribution can be very valuable.
Yes.
Hi, I'm just wondering how quantum computing will actually affect these further investigations.
It's a good question. I'm not an expert, and the quantum computing advantage has to do with certain kinds of calculation you want to do. The sort of thing I assume it will be used for is for big simulations, some big simulations which involve many particles and many variables and things, where there may be ways of speeding up current computing by a large factor, in which case using simulations might be very valuable. I don't think it would necessarily, as far as I know, would make a great deal of difference to instrumentation control at the present time. But I may be wrong in that. So as I understand it, what it enables is some particular kinds of calculation that take up too long on a current computer. So simulations of galaxy formation and evolution with many more particles than we use is a possible one, but it's quite a way off, I would thought, before that sort of advantage will be available from quantum computing. But I'm not an expert in the field, so I can't say.
Sorry, one more question, if I may. Near-Earth objects, detection of, do you see any technological advances that would make that more effective and able to detect anything that might cause a problem to us?
Yes, I'll say two things about that. One is yes, because there are automated telescopes coming up soon that will just literally scan the sky all the time with good detectors on, and then you have clever software that picks up what changes from night to night or from hour to hour. Inevitably, those are going to pick up more near-Earth objects, and our information about those will get better and better. It's already quite good, I believe, actually. And we are picking up most things. And I think we're pretty safe for the next few years, at least, which is nice to know. Although I believe in 2029 or 2028, there's going to be one coming past. You'll actually be able to see visually going past us with your naked eye. That's going to be scary, isn't it? Won't hit us, but it's the first time I've heard of it being able to be possible to actually see one of these things going past us. The only thing I'd say against that is we've got to be careful about the number of satellites we put up into space. These clusters of satellites they're talking about, and the debris from space stuff. If we're not careful, if it gets too much of that, it's going to be difficult to sort out what are them, what are those, and what are the near-Earth objects, and so on. We've got to keep a lid on that, apart from ruining our nice vision of the sky. So that's something that, but I'm astronomers are aware of that and do make a noise to try and be, RAS, for example, make quite a noise to try and make sure that people do think about that when they're proposing these constellations of satellites. Okay?
Yes, well, our autumn lecture theme is going to be on dark skies and include things like space debris and clusters of microsatellites. So we're going to be dealing with all of that in the autumn. Any more questions? We haven't quite outrun our time yet, but okay, I think okay, well, this has been an amazing tour through the technical developments of the last 100 years and a few little bit of speculation about the future. And so can we all put our hands together and thank Mike Edmunds?